Move on to chapter 16.9, and we're going to be looking at the acid-base properties of salt solutions. In this section, we want to see if we have an ionic compound that is dissolved in water. We want to know, is it going to be acidic or basic? We know that cations and anions can react with water to increase the concentration of hydronium ion, and they can also increase the concentration of the hydroxide ion. To determine the net effect, you need to look at each ion separately and then look and see if one of those is greater than the other, and then you can determine if it is acidic or basic. We will find that cations can be either acidic or neutral, and that anions, interestingly, can be acidic, basic, or neutral. So anions do have that capability of being acidic. So we'll start with anions. So anions that are the conjugate bases of strong acids will have no effect on the pH. This is going to include things like chloride, bromide, iodide, chlorate, perchlorate, and nitrate. You'll notice that I don't have the conjugate base of sulfuric acid on there because it turns out it is still acidic, and I'll show you how that fits in to the rules here in just a moment. Anions that are the conjugate bases of weak acids are weak bases, and they will increase the pH. In other words, they are basic. And we have lots of examples of those. One I'll just give you right away is the fluoride ion. And fluoride, when we put it in with water, it will dissociate and give us HF plus hydroxide. We'll find that protonated anions from polyprotic acids can be either acids or bases. And that really just depends on what the Ka of the acid is and the Kb of the base is. If the Ka is greater than the Kb, then that anion would be acidic. And that would be the case for something like HSO4-. It is an acidic anion. If the Kb is greater than Ka, then the anion is basic. And that would be something like in the case of the bicarbonate ion. So let's look at number 83 on the in-class assignment. So you can see here that I have already done the equilibrium equations for these. So here we've got the compounds sodium cyanide. Sodium cyanide, the sodium doesn't have any effect on the pH, but cyanide is the conjugate base of a weak acid, and since it's the conjugate base of a weak acid, it will be basic. And that fits in with Rule 2 as we saw on this page. So really all we need to do is we need to put in the information for the cyanide ion. The concentration of cyanide is 0.10. Water we can ignore. The initial concentration of HCN would be 0. The initial concentration of hydroxide would also be 0. This would decrease by x, so 0.10 minus x, and these would both increase by x, giving us x and x. Now, since this is the Kb of the conjugate base of a weak acid, then we're going to need to use what we learned in the last section, which is to get the Kb, we have to calculate it from the Ka on Appendix D. So I'm going to go back over and we're going to look at Appendix D 1, which has the Ka's of weak acid, and we need to look up the Ka for HCN. All right, so that's Appendix D2. We're going to use Appendix D1. So HCN is right here, hydrocyanic acid, and you'll see it is 4.9 times 10 to the negative 10. So 4.9 times 10 to the negative 10. So we're going to put 1.0 times 10 to the negative 14 divided by 4.9 times 10 to the negative 10. And we'll enter that into our calculator. So 1 times 10 to the negative 14 divided by 4.9 times 10 to the negative 10. And you'll see it's 2.04. We're going to write that as just 2.0 times 10 to the negative 5. So 2.0 times 10 to the negative 5. Well, we now have a Kb value, and we can put these things into the expression, and that's going to give us this. So 2.0 times 10 to the negative 5 is equal to x times x over 0.10 minus x. So x squared over 0.10 minus x. Now, we'll do the test real quick to see, is it okay to neglect x? Usually it is, but we want to check. So we'll do 0.1 and divide that by 2 times 10 to the negative 5. And you see we get 5,000. That tells us that x is going to be less than 5%. So I'm going to get out the red pen of neglect here. And we will neglect x. All right. Now that we have neglected x, we'll cross multiply. So we'll get x squared is equal to 0.10 times 2.0 times 10 to the negative 5. When we multiply that out, that's going to give us 2.0 times 10 to the negative 6. Well, let's go ahead and put that in. So times 2 times 10 to the negative 5. And you'll see we get 2 times 10 to the negative 6. When we take the square root of that, so we'll take the square root of our answer, we'll get 1.41. We're just going to call that 1.4. So x is 1.4 times 10 to the negative 3 molar. And since x is the hydroxide ion concentration at equilibrium, we will put OH minus. So put OH minus there. All right. Well, now that allows us to calculate the POH. So POH is equal to the negative log of 1.4 times 10 to the negative 3. And since that number is right there, I'm just going to do the negative log of our answer. And you'll see that we get 2.85. So our POH is 2.85. With that, we can now calculate the pH. The pH is going to be 14.00 minus 2.85. So 14 minus our answer, and that gives us 11.15. All right, so there we go. We've got the pH of that solution. For our next one, here we've got 0.08 molar sodium carbonate. So I have already written the equilibrium reaction. Carbonate reacts with water to give us bicarbonate plus the hydroxide ion. And we also have the expression for Kb, so bicarbonate times hydroxide over carbonate, and we'll have to calculate it using the Ka for bicarbonate. We'll get that here in a moment, but let's start with the concentration of carbonate at initial. So here it is 0.08 molar sodium carbonate. Sodium doesn't do anything because sodium doesn't affect the pH. But the concentration of the carbonate is going to be 0.080 molar. Water we can ignore. Bicarbonate is going to be 0, and hydroxide will be 0 to start with. And then for the change line, this one's going to be minus x, plus x, and plus x. So 0.080 minus x, x, and x. Now we want to calculate what Kb is going to be. So we'll use Kw, which is 1.0 times 10 to the negative 14. And Ka, we want the Ka for bicarbonate. Well, we're going to go back over. All right, don't know why I'm getting that sound, but we're going to go back over here and look at carbonic acid. So here's bicarbonic acid. Remember, Ka1 is for H2CO3, and Ka2 is for HCO3 minus. So we'll want this one 5.6 times 10 to the negative 11. All right. So I'm going to write that number down, 5.6 times 10 to the negative 11. So now I've switched back over here. We can do that calculation. So 1 times 10 to the negative 14, and we divide that by 5.6 times 10 to the negative 11. And you'll see the number we get there is 1.8 times 10 to the negative 4. So 1.8 times 10 to the negative 4. All right, so now that we've got a Kb value of 1.8 times 10 to the negative 4, we will put that in as Kb, and we'll put these values in terms of x into that expression. So 1.8 times 10 to the negative 4 is equal to x squared over 0.080 minus x. We do want to check, is it okay to neglect x? This one's going to be close, but it will work. So 0.08, and we want to divide that by 1.8 times 10 to the negative 4. And we'll see we get 444. Well, that's definitely bigger than 400. So it will be okay to neglect x. All right, so now we have neglected x. The next thing that we want to do here is to cross multiply. So we'll get x squared is equal to 0.080 times 1.8 times 10 to the negative 4. We'll multiply that out and then take the square root, and we will get a number. So 0.08 times 1.8 times 10 to the negative 4. All right, so there is the 1.44 times 10 to the negative 5, and we will now take the square root of that, our answer, and you see that we will get 3.8, so x is equal to 3.8 times 10 to the negative 3 molar. All right, that is the concentration of hydroxide at equilibrium. So there is our concentration of hydroxide at equilibrium, and then we will find that the pOH is going to be the negative log of 3.8 times 10 to the negative 3, and that's going to give us a value of 2 point something. Let's see. We'll just do the negative log of our answer, 2.42. So 2.42. Now we'll subtract that from 14 to get our pH. So 14 minus 2.42. All right, so 14 minus 2.42, and that gives us 11.58. All right, so our last problem on this particular question is, our last problem here is with part C, and you'll see that we've got a mixture that is 0.10 molar in sodium nitrite and 0.20 molar in calcium nitrite. Well, we need to get the total concentration of nitrite. And so we get 0.1 moles per liter for the nitrite from the sodium nitrite, and we get 0.2 times 2 moles per liter for the nitrite from calcium nitrite. Well, that 0.2 times 2 will be 0.4, and then plus the 0.1, and that's going to give us an overall concentration of 0.50. For water, we can ignore, because it is the solvent. The initial concentration of nitrous acid and hydroxide are both going to be 0. The concentration of nitrite will decrease by x, so 0.50 minus x. For nitrous acid, it will increase by x, as will the hydroxide ion. Now, for calculating the Kb, we will need to look up the concentration of, or not the concentration, we'll need to look up the Ka value for nitrous acid. So I'm going to go back over, and we'll find the nitrous acid, which is right there. And you'll see it is 4.5 times 10 to the negative 4. So I'm going to write that down, 1.0 times 10 to the negative 14 for Kw, and 4.5 times 10 to the negative 4. And I'm going to double check to make sure I got the right number. Yes, 10 to the negative 4. All right, well, now it's just a matter of punching that in. I think that's going to come out to 2.2 times 10 to the negative 11, but let's go ahead and do that calculation. So E negative 14 and divided by 4.5 times 10 to the negative 11. Negative 4. All right, I'm going to make sure I got the right numbers there. So 4.5 times 10 to the negative 4, that's correct. And I believe we're going to get 2.2 times 10 to the negative 11, and that is the case. Well, now that we've got that, so now that we've got the 2.2 times 10 to the negative 11 as our value for Kb, we'll put the values of the things in the expression in terms of x into that expression. So 2.2 times 10 to the negative 11 is equal to x squared over 0.50 minus x. So 0.50 minus x. We can check to see if it's okay to neglect x. I think you can see if you take this and divide by that, you're definitely going to get a number bigger than 400. It should come out to, something like 2.2 times 10 to the 10 or something crazy like that. So 0.50 divided by 2.2 times 10 to the negative 11. And you'll see, 2.3 times 10 to the 10. So it is definitely okay to neglect x. Our x is going to be extremely small here. So now we'll cross multiply. That will give us x squared is 0.50 times 2.2 times 10 to the negative 11. We'll take the square root of that. So let's clear all that. 0.5 times 2.2 times 10 to the negative 11. And then, like I said, we'll take the square root. So the square root of our answer, and that gives us x is equal to 3.3 times 10 to the negative 6 molar. Since x is equal to hydroxide, that will be our hydroxide ion concentration. And of course, we can take the negative log of that. So POH is equal to the negative log of 3.3 times 10 to the negative 6. And that'll get us 5 point something. Or, 5 point something. So let's do negative log of our answer. And you'll see we get 5.48. All right, with 5.48, we will now take, let's see, with 5.48, we will now do 14 minus that number to give us our pH. So 14 minus 5.48. So 14 minus our answer, and you'll see we get 8.52. So our pH for that solution is 8.52. All right, so we've looked at the rules for anions, and we now want to look at the rules for cations. So we'll look at our rules for the cations. When it comes to the rules for cations, we will see the cations of the strong Arrhenius bases, and that's going to include lithium, sodium, potassium, rubidium, cesium, also calcium, strontium, and barium. To illustrate this, I'm going to pull up a periodic table. All right, so here is our, zoom out a little bit there. Here is our periodic table. And so the group 1, lithium, sodium, potassium, rubidium, cesium, and then the bottom 3 in group 2, calcium, strontium, and barium, those are going to have no effect on the pH. All of these beige elements are metals, and only those 8 will have no effect on the pH. I suppose technically francium and radium will have no effect, but they're radioactive, so we're not going to mess with those. But all these other things are going to have some effect on the pH. And so only these 8 are going to be the ones with no effect. Now I bring that up because our next thing is all the other metal cations, and all those ones that I was just showing you, are going to have some effect, and they are going to act like acids. They will decrease the pH. I will explain how that happens here in just a few minutes. Some examples of things that do this include magnesium, iron, iron 2, iron 3, nickel. There's others, zinc, silver ion, aluminum ion. Just about anything that you can think of is going to do this to some extent. We will find that polyatomic cations that are the conjugate acids of weak bases will decrease the pH. They will act like acids. And so we've got an example of that would be the ammonium ion. If we have something like ammonium chloride, well, the chloride will have no effect according to rule 1 that we saw on the previous page. So the chloride will have no effect, but the ammonium will be acidic. It will dissociate to some extent in water to give us hydronium and ammonia. All right, for talking about these ions that were in Rule 5, all other metal cations, and we'll actually look at Rule 4 and Rule 5 here. So the cations of the strong Arrhenius bases, they have a fairly weak interaction with water. So there is an ion dipole interaction, but it's relatively weak, and that relatively weak interaction does not cause any significant shift in the electron density and does not do much to the pH of these, the pH of these solutions. We'll find that with the other metals, they have a very strong interaction. Most of those other metals have a significantly larger positive charge, but even like silver with a +1 charge has a bigger effect than the group 1 and the bottom of group 2. But there is a significantly strong interaction between water and those ions that causes a shift in the electron density away from these bonds, and it makes those hydrogens more acidic. You can see here that the pH of these solutions is indicated. So sodium is in group 1, has no effect on the pH. You'll see the pH there is 7. Calcium nitrate, in all of these, by the way, the nitrate has no effect because nitrate is the conjugate, it's the conjugate base of a strong acid, so no effect on the pH. So calcium nitrate, the calcium, you'll see it just barely has an effect. I had it listed as no effect, but it does technically make it just ever so slightly more acidic. But 6.9, that is so close to 7, hardly notice it. Just to kind of give you some perspective on this, the pH of the water that comes out of your tap, it will be perfectly normal and perfectly safe anywhere from about a pH of 5 up to a pH of 9. So a pH of 6.9 is hardly anything as far as a difference from quote normal. You'll notice here with the zinc has a pretty strong effect, and so the pH is down to 5.5. All right, and then with aluminum, it's an even stronger effect, and look at that. The pH is all the way down to 3.5. That is fairly acidic. That's fairly acidic. So what's happening in these is that the ions are getting hydrated by the water molecules. So this is an example of the iron 3 ion. So there's the iron 3, and it is surrounded by water molecules. There are 6 water molecules around the iron, and I'll go ahead and put the chemical formulas for those. Since iron 3 has a positive 3 charge and all of those water molecules are neutral, we will find that they are not going to. It's going to have a positive 3 charge overall. When this is present and there's other water molecules, which there are, those other water molecules can come along and just remove one of these hydrogens, and that will give us some hydronium ion. This is the resulting complex ion that we get here, and there is our hydronium ion. We can describe how much this happens using an equilibrium constant like Ka. So here is our equilibrium constant expression. It looks complicated, but it's just like what we've seen with other Kas. It's just there's a really complex looking materials there. And then here are some Ka values for some of these ions. A couple of things I want to point out about this is that you'll notice you don't see any of these with the group 1 or those bottom 3 in group 2, and that you'll also notice that for the ions that have a +2 charge, they are much weaker acids than the ions that have a +3 charge. So the +3 has a bigger effect. If you had ions that had a +4 charge in there, for example, something like titanium, titanium 4, you would see these numbers would be much higher. Okay, so now we want to put all of this together, synthesize this into one main concept. Salt solutions. Are these salt solutions going to be acidic, basic, or neutral? Well, the way to determine is we're going to use this list of rules here to determine if the overall solution will be acidic, basic, or neutral. If both your cation and your anion are neutral, then of course you're going to have a neutral solution. So neutral, neutral, you'll have a neutral solution. If you have neutral with anything else, the anything else will dictate what it's going to be. So if you have a neutral cation with a basic anion, you will have a basic solution. If you have a neutral cation with an acidic anion, you will have an acidic solution. If you have an acidic cation with a neutral anion, you will have an acidic solution. And then finally, this one is not as common, but it can technically happen. If you have an acidic cation with an acidic anion, you will have an acidic solution. All right, one last one that I want to show is if you have an acidic cation with a basic anion. Well, that depends. That will depend. And what it will depend on is the Ka of the acid and the Kb of the base. If the Ka, we're going to compare the Ka of the cation and the Kb of the anion. If the Ka is greater than Kb, then the salt will be acidic. If the Kb is greater than the Ka, then the salt is basic. Now, I've got a couple of extra problems. These are not on the normal in-class assignment. I just had written these out. And we want to determine, are these things going to be acidic, basic, or neutral? Well, sodium is a metal of our strong Arrhenius basis, so it is neutral. Chloride is the conjugate base of a strong acid, so it is going to be neutral. Well, neutral will be neutral. All right, so this one won't be acidic or basic. So sodium chloride does not have an effect on the pH. For here we've got potassium acetate. Well, potassium is a group 1 ion, so it is going to be neutral. Acetate is the conjugate base of a weak acid, so it is going to be a weak base. It'll be basic, so neutral basic, that is going to be a basic solution. Ammonium chloride. Well, ammonium is the conjugate acid of a weak base, so it is acidic. Chloride is the conjugate base of a strong acid, so it is neutral. So acidic, neutral, acidic. All right, iron chloride. Well, iron is one of those other metals. It's not in group 1 or group 2, so it is going to be acidic. Chloride is the conjugate base of a strong acid, so it is neutral. So acidic, neutral, that one is going to be acidic. Here we've got sodium bisulfate. So sodium is neutral, and bisulfate is hydrogen sulfate ion. It is actually a pretty significantly strong, although technically still weak, acid. So it is acidic. So in this case, this is going to act as an acid, and so that means this will be acidic as well. Our final one here is ammonium, which is acidic, and fluoride, which is basic. Well, the answer here is it depends. So in order to determine overall, is this going to be acidic or basic, we need to get the Ka of our acid, so the Ka of NH4+, and we need to get the Kb of our base, which is the fluoride ion. Well, the Ka of ammonium is going to be equal to the Kw, which is our constant, our ion product constant for water, and the the Kb of NH3. So the Kb of NH3. All right, that looks really ugly there, so I'm just going to try to fix that real quick. So Kb of ammonia. All right, so let's put in some numbers. So 1.0 times 10 to the negative 14. And our Kb for ammonia, I'm going to pull up our appendix. And we want the Kb for the base, so there is 1.8 times 10 to the negative 5. All right, so we'll come back over here, and now we can punch those numbers into our calculators. So 1 times 10 to the negative 14, and excuse me, 1.4 times, or 1.0 times 10 to the negative 14, and we will divide that by 1.8 times 10 to the negative 5. And you'll see that gives us 5.6 times 10 to the negative 10. Well, now we're going to look at Kb for fluoride. Well, that is going to be equal to the Kw over Ka for HF. So Ka for HF. Well, Kw we already know is 1.0 times 10 to the negative 14. And then Ka for HF, I'm going to pull it up. So here is HF right there, 6.8 times 10 to the negative 4. So 6.8 times 10 to the negative 4. Okay, so let's go back to our in-class, or not our in-class, but on my document camera here. And we'll do 1 times 10 to the negative 14, and then we'll divide that by 6.8 times 10 to the negative 4. And we'll see that gives us 1.5 times 10 to the negative 11. So 1.5 times 10 to the negative 11. Well, now we just need to determine which one of these numbers is bigger. It's the bigger one. So since that's the bigger one, Ka, this solution is acidic. And again, it's just look at the value of Ka versus Kb. Whichever one is bigger will dictate the P, will dictate what the answer is going to be. All right. Well, we're going to stop this video here, and we will start a new video with section 10.